Good day, everybody, and once again, your favorite uncle is back. And today we are going to be discussing the physical science exam from May-June 2023. So if you have not subscribed, please just make sure you're part of the family. Right, so let's go right into the exam. Right, so we start with the multiple choice section. Right, I'm going to delve into the first question. They say, which one of the following quantities is the tendency of an object to resist change to its state of motion? So in that case, that is the inertia. All right, I hope that we know that by now. Okay, so that's the inertia of a body. Right, so question 1.2 says, a ball is dropped from rest at a height above a concrete floor. They say the ball strikes the floor and bounces vertically up and down on the same spot of the floor. Right, now, so I want us to discuss, first of all, what would be happening on this ball. They say the velocity time graph for the bouncing ball is shown below, with point P, Q, R, and S representing different times during the motion. So if we have a look at this, right, so which means if we were to consider that to be the ground, we would have dropped the ball, right? And here it is. It has a velocity of 0 at the time where we release it, where we drop it. And the velocity increases. Of course, this is as the ball goes down, right? And so P would represent the first instance when the ball actually touches the ground, okay? So if you look at that, that's the velocity just before it lands on the ground. So that would be the velocity over here, just before the ground. And this is the bouncing velocity. So this is just after it leaves, as it leaves the ground, right? And now what happens? At point Q, this is where we are reaching the first maximum height. So in this case, so that was point P. This is point Q. Right, and of course point R is when it bounces again, right, when it lands on the ground once again. So this would be R, and S would be another maximum height, and that is where that graph actually leads us. Right, now they're asking at which point does the ball reach its maximum height after the first upward bounce. Right, so at which point does it reach its maximum height? That is at Q. Remember, it reached its first bounce at point P, and in that case at Q we reach maximum height. So that would be B, that would be our answer there. Right, and so the next question, they say two blocks P and Q of masses M1 and M2 respectively are held at rest on a frictionless horizontal floor with a compressed spring between them, right, as shown below. So they say when the blocks are released and the spring drops to the floor, block Q moves to the right and with a velocity V, right? So this guy goes to the right with a velocity V, okay? And they say which one of the following represents the momentum of block P after the blocks are released. Right, now I want you to note, ladies and gents, so firstly, block Q will have a momentum of M2 multiplied by V, right? If we consider that to be a positive direction. So in this case, remember that because their initial momentum was 0, right? So the sum of their momentas before was equal to 0, right? And remember that will be equal to the sum of their momentum after, right? So in that case, that would be 0. So as a result, it means that the momentum of P will be equal to the momentum of Q afterwards, right? So now, which means if I were to measure the momentum there, it should also be equal to M2V, but in this case, it should be to the left. Okay, so what I'm going to do there is that I'm going to choose B, which one is to the left? M2V to the left. So in that case, right, I'm going to choose that answer over there. Right. And that is all because remember their masses are different. Okay, they told us that they've got mass M1 and M2 respectively. So in that case, it would mean that P would also have a momentum of M2V, but in the opposite direction. All right, so let's go to the next one. So they say the magnitude of the gravitational force that spheres X and Y exert on each other is F, right? Now they say to us the mass of sphere X is now doubled, okay? While the mass of sphere Y and the distance between the centers of the spheres remains the same. Right, now they want to know which one of the following combinations is correct for the magnitude of the forces, right, that the spheres now exert on each other. Now remember that the forces would be equal, first of all, right? That's according to Newton's second law, right? Body A, if body A exerts a force on body B, this time body X on Y, right? So body Y will exert an equal but opposite force on X. So firstly, we had a force F, but now we double the mass, right, of one of them. So they say the sphere, the mass of sphere X is now doubled. So that would mean that the force will also double. Why? Because force is directly proportional in this case to the mass of the object according to Newton's law of universal gravitation. So our answer will be 2F and 2F respectively. Okay, right, so I hope that makes sense. Next question, they say hot air balloon is moving vertically upwards at constant speed. Please remember, at constant speed, it means that our acceleration is 0, and as a result, net force is 0. Right, they say which one of the following physical quantities associated with the hot air balloon changes during its motion. Right, so remember the weight remains the same, momentum remains the same because the speed is constant and so is the mass. The kinetic energy remains the same because again that is related to the velocity. But of course the balloon is ascending upwards, so the potential energy would change because the position of the balloon relative to the ground keeps changing. So that is going to change. Right, the next question, they say a learner standing at a roadside records the frequency of sound waves produced by the siren of an ambulance. The ambulance is moving at constant velocity with a straight along a straight horizontal road. The frequency versus time graph of the detected sound is shown below. Right, now they say which one of the following statements concerning the motion of the balloon is correct. The motion of the ambulance. I'm still seeing balloons, ne? Right, is correct. So they say the ambulance, right, firstly, approaches the learner and then passes the learner. Okay, now, look at that, ladies and gents. First of all, I see that the detected frequency is lower. At first, it suggests that this is something that was moving away, right? And in that case, afterwards, the frequency is much higher, so that means that it was moving towards. Now, so approaches the learner, not really, so that would not be correct. So firstly, they say moves away from the learner, then turns and approaches the learner. That looks just about correct, but let's look at the other answers. So they say approaches the learner, then turns to move away, not really, moves away from the learner and then stops. Okay, right, so in this case, remember we didn't know what they told us that the ambulance is moving at constant velocity, right? So I will assume that it continues to move. So the only one that looks plausible is actually B. Okay, right. So next question. They say we've got two identical charged spheres, X and Y, that carry charges 2Q and negative 6Q respectively. Right, they say the spheres X, or sphere X rather, experiences an electrostatic force F rather to the right when the distance between their centers is R. Now, okay, so now they say the spheres are brought into contact and then returned to their original positions. Right. Which one of the following represents the magnitude of the electrostatic force that sphere X experiences now? All right, so first of all, ladies and gents, let's do this. So it means that the force that would be experienced by X at first would be 2Q multiplied by 6Q, right? Regardless of the, the sign of the charge, in this case, divided by R squared. So that means that F would be K, 6 times 2 would be 12. So I'll say 12K Q squared divided by R squared. Now remember, the moment that the charges or the spheres touch, right, they will now share the charges equally. So which means the new charge, right, let's call that the net charge, will be equal to, it will be 2Q plus a negative 6Q divided by 2, right? So if we take that, minus 6Q plus 2Q gives us a negative 4Q, divided by 2, that will give us negative 2Q. So meaning both spheres will have a new charge of negative 2Q coulombs, right? So which means now the new force, and I'm going to state new, so I want to relate the new force in relation to F. So the new force will be K, now note, it will be 2Q times another 2Q, right? So it will be 2Q squared divided by R squared because it was placed exactly at the same place. So now we've got 4, right? That's KQ squared divided by R squared. So this is the new force. Okay, ladies and gents. Now, if I look at this new force, can you see that it is now, okay, if we look at the old force, right, force F, it was 12, and this one is 4, so which means it has been divided by 3. So if I were to divide the old force by 3, it would give me this new force. So I can say this is the same as saying 1 over 3 times 12 KQ squared divided by R squared. Now, if you take 1 over 3 times 12, that will give me 4. So I wouldn't have changed anything, right? So which means this is the same. The new force is actually 1 over 3 times the old force, F, right? So in that case, the correct answer would therefore be B. Right, I hope that made sense, ladies and gents. Right, as we move right along, they say in the diagram below, we've got R1, R2, and R3, which are identical resistors. The battery has negligible internal resistance. So they say the power dissipated by R1 is P, okay? And they want to know which one of the following is the power dissipated by R2. Now remember, we've got identical resistors. So supposing I said to you, the current passing through them was I, right? So remember what's going to happen. Because they are identical resistors, the current passing through R2 would be I over 2, okay? Right, now in this case, remember power is equal to, let me relate power to current. So this would be I squared multiplied by R. Okay, so P, the power on P1, right, on R1 rather, would be I squared times R1. But remember, R1 is equal to R2 is equal to R3. So I might as well just say I squared R, right? Now on R2, the power, okay, let's call it, let's call it P2. P2 will be I over 2, right? Remember, this is squared, multiplied by R. Remember that the resistance remains the same, isn't it? So I've got now I squared R over 4. Okay, so can you see that now it is actually, P2 is actually P, remember P was I squared R over 4. Okay, so that would be 1 over 4 times P. So that is going to be A, ladies and gents. Right, as we move right along, they say the simplified diagram below represents a DC motor. Okay, so they say the diagrams below indicate some changes made to the above motor. Right, so what do they want to know? They want to know which of the changes to the motor above will change the original direction of the rotation of the coil. Now, without necessarily just making things difficult for ourselves, right? So we know in this case the direction of the current would be in that way. The direction of the field would be from north to south. Current moves from positive to negative. That's as per conventional current, right? So in order for us to maintain the same direction, right, if we make any changes, we have to make changes both on the magnetic field as well as on the current. If I change one of them, then it will definitely change the direction of rotation, right? So let's look at diagram 1. All right, so they've changed the orientation of my magnets. So my field changes, but the current is still the same, right? So definitely that will change the direction. Okay, on diagram 2, okay, the field remains the same. We are going to from left to right, but the current is now changed. So from positive to negative, and my positive, the polarity has changed, right? So definitely that will change the direction. So in diagram 3, now what did they do? They changed the magnetic field from right to left, and again they have changed the direction of the current. So that will not change the direction of rotation. Why? Because I've changed both my variables in this case. So definitely it should be 1 and 2 only, right? So that will be it. Okay, right, I hope that makes sense, guys. And finally, 1.10, they say an atom has a ground state at X. Okay, so if we were going to draw this, so it has a ground state at X, and they say when the atom moves to a higher energy state. So if we suppose that this would be a higher energy state, okay, so that's our ground state X, and it moves to a higher energy state Y, they say a line spectrum is observed. So remember that atom is actually moving from ground to, in this case, a higher energy state. Now, remember, for it to do that, it must actually take energy, right? It needs energy rather to do that, to go from ground state to higher energy. And so what it would tend to do is that it would tend to absorb energy, right? So they say to us, which one of the following combinations is correct for the energy change of the atom, the type of line spectrum observed during the transition, right? So remember that it has moved from X to Y, right? And in this case, it means that it would be a line absorption spectrum. So I would say from X to Y, okay, the energy change that it would experience, right, would definitely, okay, higher energy and minus lower energy. So in that case, we'd say, right, from X to Y, it's the is the energy change, right, and it would be minus rather, and so it would be an absorption spectrum. So that is C. And sorry, my voice almost went away there. And now we move on to question 2. Right, on question 2, they say the block A rather of mass M is connected to block B with a mass of 7.5 kilograms by light inextensible rope. So remember, once we say light inextensible rope, it means that we will not consider the mass of the rope as part of the mass of the system, right? So inextensible simply means that the maximum tension will be taken as the force that is used to, to pull the rope in this case. So they say it is passing over a frictionless pulley. Very important, because it means that the tension on the one side of the pulley will be equal to the tension on the other side of the pulley. Right, they say block B is initially held at a height of 1.5 meters above the ground, and while block A is initially stationary on the ground, right, as shown in the diagram below. All right, so ladies and gents, what do they tell us? They say when block B is released, right, it moves vertically downwards. Okay, so block B would go down and strikes the ground with a velocity of 3.41 meters per second. So it will reach this point here at 3.41 meters per second. Remember, its initial velocity would have been 0. Okay, so they say ignore the effects of friction. Right, now they ask us to show by calculation that the magnitude of the acceleration of block B was 3.88 meters per second squared while the block was moving vertically downwards. All right, ladies and gents, so I am going to use equations of motion there, right? So for 2.1, I'm simply going to say, right, so my initial velocity was 0. My final velocity is 3.41, and I know the height there. So I would use, in this case, the equation of motion v squared is, vf squared is equals to vi squared plus 2 times a delta y, right? That's the displacement in the vertical direction, right? So my final velocity, remember they said this is 3.41, right, squared. My initial velocity was 0. My acceleration is what I want, and my displacement is 1.5. Okay, so let's do our gymnastics over there, right? So I'm going to say, right, this is 3.41 squared. Okay, and on the right hand side, I've got 2 times 1.5, which is 3, right? So I've got 3a, so I can divide by 3 on either side. What I do on the left, I will do on the right. And so what will be my, so that's divided by 3. And in this case, you can definitely see on my calculator there, my acceleration is 3.88 meters per second squared. Okay, so let's show that dot there. Okay, so that's 3.88 meters per second squared. Right, and off to the second question. They say to us, draw a labeled free body diagram showing all forces acting on block B immediately after it was released. Now remember, as block B goes down, What are the forces? So I said to you, please note, the Mach allocation tells you how many forces you should expect there, right? So for 2.2, I'm going to have, okay, so let's try and do that nicely there. So this would be the tension on the string, and please label in full, tension of the string. Okay, and what other force is acting there? That would be the gravitational force, right? It is what's pulling this guy downwards. And please try to indicate as much as you possibly can which force is bigger than which. I've tried to show there that the gravitational force is definitely greater. So that means that that body will accelerate in the direction of the greater force, and that force is definitely the gravitational force. Now, the next question says, state Newton's second law of motion in words, right? Please remember, ladies and gents, we simply say that a body will, if a resultant force acts on a body, the body will accelerate in the direction of the resultant force, right? And that acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object, right? Another way of stating that, which is a little bit shorter and neater, right? It says the resultant force acting on an object is equal to the rate of change of momentum of that body, right? Okay, so those are the two ways in which we can state that, okay? In that case, I will not necessarily write that down. Okay, let's go to the next question. They said, calculate the value rather of m by applying Newton's second law to each block while they are in motion. Now, so we already have the free body diagram for block B, right? So for block B, I'm going to start with that one. I will simply say, well, I know, so that's 2.4, right? So for block B, I will say, well, F net is equal to MA, but what is the sum of forces, right? For block B, I'm going to consider downwards as positive. You always take the direction of motion as positive, okay? So this is going to be the force of gravity, okay, for block B, minus the tension on the string. Okay, and this will be equal to MA. Right, so let's substitute all that we know for block B. Force of gravity is mass, which is 7.5 times gravitational acceleration. So this is going to be 7.5 times 9.8 minus the tension is unknown, and this is equal to the mass of the body, right, which is 7.5 multiplied by acceleration. And in this case, we already know what the acceleration is, right? The acceleration was 3.41. Okay, right, so we can find the value of the tension. Okay, where is my calculator? So I'm going to say 7.5 times 9.8, and I'm going to subtract. So I'm going to bring this all on the left hand side and t to the right hand side. Okay, so this would be minus 7.5 times 3.41. Okay, that's the no, actually not 3.41. Our acceleration, sorry, was I wrote 3.41. That was the velocity. Acceleration was 3.88, right? So let's correct that. So that's 3.88. So my tension is 44.4, ladies and gents. Okay, so yeah, so that would be, Okay, so this guy is misbehaving now. Okay, so that's 44.4 newtons, right? So this is for block B. So now going into block A. So for block A, so remember, what will happen now for block A? Let me try and remove all of these khokakis, right? So for block A, remember now, I've got F net is equals to MA. So remember, block A is going upwards. So the force that is pulling block A up, it's accelerating up. So it means tension must be greater than the gravitational force, right? So for block A, it's going to be the tension minus the gravitational force, so F gravity. Okay, this is equal to MA, right? So this is the mass of A, right? All right, so this would be now, remember it's a frictionless pulley, so it means the tension on the one side would be equal to the tension on the other side. So this is 44.4 minus the force of gravity on this guy is 9.8 m. Remember the mass is unknown, and this would be equal to, okay, let me try and make some space there. So this would be 44.4 minus the force of gravity. We said this is 9.8 m, right? And this is equal to 3.88. Now remember, acceleration is upwards, but we are considering for A that upwards is positive. So this would be 3.88 m, right? So if I take the 9.8 m to the other side, they will add together. Okay, so 9.8 plus 3.88. And that gives me 13.68 m. Okay, and if I divide both sides by 13.68, sorry, that's 68 over there, that cancels with that, and the mass of our object is 44.4 divided by 13.68, and I get a mass of 3.25, right? So the mass would be 3.25. And this is in kilograms. Right, I hope that makes sense, guys. I am trying by all means to answer this question on here, right, so that it's easy for us to follow. Right, so finally they say to us, calculate the maximum height above the ground reached by block A. Okay, now I know if you look at this question, it looks somewhat ridiculous, right? Because if you think about it, you'd say, well, if this guy goes 1.5 meters down, well, block A should go 1.5 meters up, right? And in that case, why would we want to bother? Why would it be 5 marks? But I want you to really think about it, ladies and gents, and I want you to listen very carefully. That the moment block B strikes the ground, right? In this case, A was at a velocity, it's the same velocity, it would have been at a velocity of 3.41 meters per second, right? But it won't stop immediately. What will happen to A? A will continue moving up until it stops at its maximum height, okay? So what you consider there is that what would have happened to A is that it moved a vertical height of 1.5, sorry. So that was 1.5 meters, right? And then once it gets to this point with a speed of 3.41 meters per second, then it goes again a certain height until its velocity is equal to 0. Okay, so they want to know that maximum height above the ground. So let's find out what this height will be, right? And this time, remember, it's not moving because it's pulled, but it is moving due to gravitational acceleration. Why? Because block B would have been on the ground. Okay, so I'm going to find out what is my maximum height. So I just wanted to take a different color there, right? I'm going to find out about this maximum height, and I'm going to add it to the 1.5. So let's do that. So my initial velocity is 3.41, right? Which is the same as velocity of B, of A rather. It would actually B, right? So in this case, final velocity is 0 and acceleration due to gravity. So I'm going to use the same equation. Vf squared is equal to Vi squared plus 2 times G this time around, okay, delta Y. Okay, final velocity is 0 squared. Initial velocity 3.41 squared plus 2 times. Now please note, in this case, I'm considering upwards motion as positive, but remember that gravity always acts vertically downwards. So this would be minus 9.8, and I'm looking for that displacement. So I'm going to take this to the other side, minus 3.41, okay. So this will be minus 3.41 squared equal to 2 times 9.8, negative 9.8. That would be negative 19.6 delta Y. And if I divide by negative 19.6 on either side, negative 19.6, what do I get? Okay, ladies and gents, so I've got negative 3.41 squared. I'm going to divide that by negative 19.6. Okay, so I get a displacement of 0.59 meters. So what is the maximum height above the ground? So therefore, maximum height will be equal to 1.5 plus the 0.59, and so this will be 2.09 meters. Okay, I hope that makes sense, guys. And essentially, that is how the cookie crumbles in this question. Right, and off to question 3. They say ball A is dropped from rest, right, from the top of a building which is 15.2 meters high. Right, so they say to us after ball A has fallen 3.2 meters. Okay, so we need to note that after it has fallen 3.2 meters, right, a second ball B is projected vertically upwards from the ground, and after a while the 2 balls strike the ground at the same time, and they say ignore the effects of air resistance. Right, so the first thing that they ask us there is to define the term free fall. So remember that free fall, this is the motion of an object under the influence of gravitational force only, right? Please don't forget that operative word only. Right, so first of all, they ask us to calculate the time taken for ball A to strike the ground. Now, ladies and gents, what I'm going to do is I'm going to first look at A, right? So we're looking for A there. We know that the initial velocity would be 0, right? And by the way, I'm going to take downwards motion as positive. So the initial velocity for A is 0. They told me that it is dropped from rest. Okay, so the final velocity is unknown. I don't know the velocity when it gets to the ground. Gravitational acceleration, remember, it will be positive because we've taken down as positive, and gravitational acceleration is always downwards, right? So the time also unknown, but in this case I know the displacement, right? It would have been displaced from the top of the building to the ground, which is 15.2 meters, right? So, and that is positive because it is displaced downwards. So let's do that. So we are looking for time, right? And what do we not have? We don't have the final velocity. So which equation of motion? I'm going to use delta y, the only one without final velocity. So that's vi delta t plus 1 over 2a delta t squared. Right, let's substitute. That's 15.2. My initial velocity is 0, so that makes that whole term 0. That's half of 9.8 times delta t squared. Right, so quickly, half of 9.8 gives us 4.9. Delta t squared is equal to 15.2. And we're going to divide by 4.9 on either side and take the square root. Okay, so let's do that quickly. So I'm going to say this is 15.2 divided by 4.9. Okay, and I'm going to take the square root of that answer. That gives me 1.76. So that means that delta t, remember to take the square root, that would be 1.76 seconds. All right, I've tried to squeeze that in there, right? I hope that it does make sense. So let's go to the next question. So they say the magnitude of the velocity, okay, they say calculate rather the magnitude of the velocity with which ball B was projected from the ground. Now I want you to remember ball B was projected only after A has been moved 3.2 meters from its original position, right? So the time that B will take, remember, and they land on the ground at the same time. So if we can find the difference of time that A took from that position there, 3.2 meters below the original point to the ground, okay, then I would find the time that it took for B to travel, right? So in this case, I'm going to simply say, ladies and gents, so first of all, if I look at ball A, right, for ball A, right, so I'm looking for the time that it takes till this point over here. Right, so again, our initial velocity is 0. Okay, I'm going to use the very same equation of motion. And this time around, delta y vi delta t plus 1 over 2a delta t squared. Right, but my displacement is 3.2. Okay, my initial velocity is 0 and makes that whole term 0. That's half of, again, 9.8 delta t squared. So I'm not going to waste much time there. Okay, so I'm going to say 3.2. This is divided by 0.5 times, no, let me put that in brackets. So this is divided by 0.5 times 9.8. Okay, and that answer, I'm going to take the square root of that answer, and that gives me 0.8. So the time that it took for A to get to this point here was 0.8, let's say 0.81 seconds. So meaning the remaining time that it took for B, or rather the time that it took B to get from the ground and back to the ground again would be 1.76 minus 0.81. I hope that makes sense. So I'm going to say 1.76 minus 0.81, 0.81, and so that gives us 0.95 seconds. Right, so that's the total time of flight for B, right? So, but we're not interested in the time of flight. What are we looking for? the velocity with which it was projected. Now think about it, ladies and gents. So which means B went up and then came down. And how long did it take for it to do that? Right? It took 0.95 seconds. But we remember this would be a time symmetry, right? So in this case, the initial velocity with which B leaves with first would be the same as the final velocity it comes back to the ground with, which we don't know, right? But also what it means is that we've got a maximum velocity, a maximum height, a velocity at maximum height of 0. So the velocity when it gets to that peak is 0, right? But also note that the time that it takes, right? If I were to call this P and I call this Q and I call this R, the time that it takes from P to Q would be the same as the time that it takes from Q to R. So what I'm going to do is I'm going to consider motion from P to Q. Okay, so in that case, my initial velocity is unknown. That's what I'm looking for. My final is 0, but I know the time and I know the acceleration. So this is going to simply say Vf is equals to Vi plus G delta T. So my final velocity is 0, maximum height. Initial velocity, that's what I'm looking for. My gravitational acceleration, please remember we've taken down as positive. So this continues to be 9.8. And the time, delta T, is, well, the time that we calculated. Now, actually, please remember, so it will be half of this time, right? Why? Because of the fact that we only took from P to Q and not the entire motion of body B, right? So 0.95 divided by 2, actually, I don't know why I removed that, divided by 2, this would be 0.475, right? Okay, let's try and squeeze that in there. So 9.8 times 0.475, okay, and multiplied by 9.8, and I get 4.666. So our initial velocity, and I'll get a negative answer, right? Negative 4.66 meters per second. By the way, why is my answer negative? Because in that case, it was going up. And so as a result, they just said the magnitude of it. So that would be 4.66 meters per second. But we know that it was going upwards and its velocity was initially negative, right? Okay, let's go on to the next point. So they say to us, on the same set of axes, right, draw a position time graph to show the motion of both ball A and ball B from the instant that ball A is dropped until the time it reaches the ground. Right, so ladies and gents, what I'm simply going to do there, okay, so I am going to, remember we're talking about position versus time. Okay, so position, that's in meters, and time, that's in seconds, right? So what I'm going to do, let's start with A, right? I'm going to use a blue color for A. A was just simply, dropped, okay, from that position above the ground, and in this case until 15.2. Okay, so in this case, it means that this would be the position versus time graph. Now, at this point here, I know that this would be my the time that it took, 1.76. So that would be 1.76 over there, right? But remember, at some point, we had moved, so the height there was 15.2. So that's 15.2. Sorry that I don't have as much space. 15.2. Now the height at this point here would be that 3.2 difference there. So what's 15.2 minus 3.2? That would be 12, right? So this would be 12 meters over here. Okay, and we know it was at that height when it had traveled, we said 0.95, right? 0.95 seconds. So the difference there should actually be 1.76 minus, no, actually we said that that's 0.81, right? And so we said 0.81, 1.76 minus 0.81, that was 0.95. Okay, so remember, so this would have been at 0.95. Okay, right. And so that was 1.76. Yeah, I think I squeezed myself a little bit too tightly there. Okay, so what about B in this case? So remember, B only started moving when A would have been at that height of 0.95, okay, or 0.81 rather, okay. It took 0.81 seconds to get to this point, okay, but in this case, it means the total time of flight for B would have been 0.95, okay. Right, in fact, I did something incorrect there. This would be 0.81. Sorry about that, ladies and gents. And that would be 1.76. Okay, so B only started from that point. Okay, so I'm going to use a different color for B. And it came back to A, right? And remember, it would have taken 0.95, so it started from this position, right? I don't know the height that B will actually reach, okay? But I do know that it will. Okay, so I'll just draw a position versus time graph that looks something like that. Okay, right, it started from the ground and it reached the ground again. Okay, so in this case, I know that it would have taken that time. As I said, I don't know the maximum height that it reached, but we do know that it traveled for 0.95, right? Okay, so they said to us, what do we need to show? They said take the ground as 0, label A and B. So we need to do that. So the blue graph is A and the red graph is B. Okay, and they say clearly indicate on the graphs the starting time of each ball, right? So the starting time for A was 0 and the starting time for B was 0.81. And they say the initial position of each ball. So the initial position would have been 0 for B and 15.2 for A. And they say the time that the balls strike the ground, that's 1.76. And essentially, ladies and gents, that is really how the cookie crumbles. Okay, I hope that that graph makes sense, even though I try to squeeze it within a small space. Please don't forget to label your axes, very important there, your position as well as your time in seconds. Right, and we'll go to the next question. Right, on question 4, they say that trolley A of mass 7.2 kilograms moves to the right at 0.4 meters per second. It's indicated there on the diagram. They say in a straight line on a horizontal floor. It collides with a stationary trolley B of mass 5.3 kilograms. Okay, and they say after the collision, the trolleys lock together and move to the right as shown in the diagram below. They say ignore the effects of friction, any frictional effects. So in this case, firstly, they say state the principle of conservation of linear momentum. We know in an isolated system, the total linear momentum is conserved, right? Okay, or you can say in an isolated system, momentum before collision equal to momentum after collision. Right, so let's go to the next question. 4.2, they say calculate the magnitude of the velocity of the trolleys immediately after collision. So, ladies and gents, we know that we're going to apply the principle of conservation of momentum. So we're saying the sum of their momenta before collision will be equal to the sum of their momenta after collision. Right, now before collision, we know that the mass of A, velocity of A, they were, they were separated. But we know that B was actually stationary, right? They told us that it collides with a stationary trolley, which was B. But after collision, we know that the two trolleys are going to move together. So I'm going to add their masses together, and they've got the same final velocity, right? So that's initial velocity there. Now let's substitute the masses. That's 7.2. So I'm going to consider direction to the right as positive. So please always keep that in mind to choose direction as positive. So that's 7.2 times 0.4, right? Plus this is going to be 0. And this is going to be 7.2 plus 5.3. And we're looking for that final velocity. Right, so without wasting any time, I am going to calculate on my left-hand side. I've got 7.3 multiplied by 0.4, and I've got that there. And I'm going to now divide it by the sum of 7.2 and 5.3. Okay, so I get a velocity there of 0.23, yeah, let's say 0.23 meters per second. And I get that velocity to be positive, and so it means that it is to the right as well, right? So in this case, 0.23 to the right. Okay, so that is the velocity. Please don't forget to mention direction, because, oh well, they said magnitude, so we didn't necessarily need to mention direction. So that's 4.2.1. So 4.2.2. So they said calculate the average net force exerted by trolley A on trolley B during the collision if the collision time is 0.02. So we want the force. So we're going to use the impulse momentum equation, right? So F net delta T, that's equal to the change in time, in momentum. So remember, we're going to only look at one of the trolleys, right? So because I'm looking for force, they've given me the time to be 0.02, right? So they said the average net force exerted by trolley A on trolley B, right? So I'm going to take the change in momentum of trolley A, right? So in this case, trolley A has got, remember, the change in momentum, that's mass times, the change in velocity. So the mass of trolley A, that was 7.2. The final velocity of trolley A is 0.23 minus the initial velocity of trolley A, that was 0.4, right? If you had used trolley B, that would have been 0, right? Sorry, not 0. The final velocity would have been 0.23, but that would be minus 0, right? And the mass we would have used 5.3. And you should be able to get the same answer either way. So I'm going to divide that by 0.02. What I do on the left, I do on the right. So my net force would be, So let's say 7.2 multiplied by, so I've got 7.2. Okay, so I made an error there. So that's 7.2 multiplied by the difference of 0.23 minus 0.4. Okay, and I'm going to divide all of that by 0.02. Okay, I get a force of 61.2 newtons, right? So I get that to be negative because remember, we've taken that direction to be positive. So definitely trolley A experiences a force in the negative direction. But because they said the magnitude, this doesn't matter to us. So this is simply going to be 61.2 newtons. Right, and that's how the cookie crumbles, ladies and gents. Right, and off to question 5 we start. So they say to us we've got an electrical motor which pulls a 20 kilogram crate from rest. So we know this guy is going to move from rest. And they say at point A, up an inclined plane by means of a light inextensible string. So again, we've got that light inextensible rope there, which is telling us that the mass of the rope will not form part of the masses of the system, right? They say the inclined plane makes an angle of 18 degrees with the horizontal. B, C, and D are points on the inclined plane, and the distance between A and C is 15.6 as shown on the diagram. Now, first of all, they say to us, the motor exerts a constant force of 96.8 newtons parallel to the inclined plane on the rope, right? And again, they say constant frictional force, so we know the force that is applied and we know the frictional force that acts on the rope as it moves on the inclined plane. Now they say define a non-conservative force. So remember that non-conservative force are forces whose work done depends on the motion, or rather on the motion of the object, okay, or on the path taken. That's the correct one. Okay, so in this case they say use energy principles to calculate the speed of the crate when it reaches point C. Now, ladies and gents, I'm going to use my work energy theorem. Now, I know that the net work done will be equal to the change in kinetic energy, right? We're looking for the velocity when it gets to that point C there, right? So now, and I know that it actually is going up, so which means the forces that are winning must be the forces that are actually going up. Now, what are the forces that are acting on the trolley, right? So firstly, I know that I've got the applied force, so I'm going to put that there. I've got the force that is applied. I've got frictional force, right? They've told me that there's friction here. That's kinetic friction. Minus, in this case again, we've got we've got gravity parallel, right? So I'm going to take the parallel component of gravity, and I've got the normal force as well as the perpendicular component of gravity, right? Now, if you didn't want to add the perpendicular component of gravity, if you didn't want to add those components, you can remove both of them and replace them with just the one gravitational force when they ask you to draw a free body diagram, right? So what you do is remove this guy and that guy and replace it with that just one force over there, right? So now they say to us, okay, we've got, and by the way, please never draw as I've drawn there. I've drawn both of them, so I'm going to remove force of gravity and just leave the other forces, right? So that force applied is the force of the motor. Okay, so I'm going to say, right, for the net work done, this is equal to F net multiplied by delta x, the cos of theta, and this would be half the mass, final velocity squared, minus initial velocity squared. Right, so what is my net force? We said it's the force applied minus the friction minus Fg parallel. So what I'm going to do, let's calculate the net force on the side. We said that's force applied. We are taking upwards motion as positive, up the incline as positive. So that's force, let's call it the force of the motor, minus Fg parallel, minus kinetic friction. Right, so force of the motor, they said that was 96.8 minus, now remember, Fg parallel would be mass times gravity, the sine of 18. So that would be, mass is 20 times 9.8, the sine of 18, but this is minus the friction as well, which is 13.5. So if we take all of those forces, right? So 96.8 minus 20 times 9.8, the sine of 18. If you don't know where this comes from, please go and watch my video on work, energy, and power. Okay, so that gives us 22.76, right? So I'm going to take that entire value, 22.73 rather, dot, until whatever newtons, right? So this is multiplied, so it's that value, 22.73, dot, times the displacement is 15.6, the cos of. Now, ladies and gents, remember that our net force is actually upwards. Why? Because this guy is accelerating up. Okay, they didn't say it's moving at a constant speed and it's going upwards, right? So in this case, it would be the cos of 0. Remember that that's the angle between direction of motion and the force in question. So this is going to be half, the mass is 20, final velocity is what I'm looking for, and my initial velocity is 0, so that would be easier for us to find. So we're going to divide both sides by half of 20, which is 10, so divide by 10, and we're going to take the square root to find that final velocity. Right, so let's do that. Actually, why did I remove that answer? Okay, right, my answer will be slightly affected because for some reason I just removed that entire answer there that I'd calculated. So this would be 22.73. Okay, please try not to try not to take to round off. That's what I want to say, to round off during the course of your calculation, right? So this is going to be cos of 0, but you know cos of 0 is 1. Okay, so this is divide by 10. Okay, I've got that answer there, which is 34.09, and all I'm going to do is take the square root of our answer, and that gives me 5.84 meters per second, and that is how we'll get to that answer there. Of course, please just make sure that you try and get this answer back. Right, now they say to us, calculate the minimum average power dissipated by the electric motor to pull the crate from A to point C. Now guys, I want you to please keep this in mind, right? So when I calculate the power, I know that power is the rate at which work is done, right? I'd have to calculate the work done by the motor and the time that it takes, right? But in this case, I am going to use, so for 5.3, going to say, right, power is also equal to the force. Now I'm looking for the power, right, the average power dissipated by the motor. So it would be the force of the motor multiplied by the average velocity. So in this case, please keep this in mind, 96.8. How do I get my average velocity? It would be the sum of my velocities between A and C, right? So it would be velocity of A. So let me write that down. So that's Fm into velocity at A plus velocity at C divided by 2. That's the average velocity, right? So that would be my velocity at A is 0. Okay, my velocity at C is the one that I just calculated, 5.84. And this is divided by 2. Okay, so let's calculate there. Okay, so 96.8 multiplied by, so that's into 5.84 divided by 2. That gives me an amount of power of 282.66. Remember, power is measured in watts. Okay, so that is the power that is dissipated by that motor. Okay, so let's go to the next question. They say when the crate reaches point C, the rope breaks. The crate continues moving up the inclined plane, right? Comes to stop at D and then slides down the plane past point B. Right, now they say to us, draw a labeled free body diagram for the crate as it slides down the plane past point B. Right, so remember that the rope has now snapped, okay? So it is now moving and the rope is no longer a part of that entire equation. Now, what are the forces that are acting? Right, so now as it slides down, remember we still have friction that's acting. But now we've got gravitational force, the parallel component of gravity. Right, friction is opposing the motion. Right, they said a free body diagram, and we're going to get to that in just a little bit. Okay, so let me just draw it over there. Okay, so I would have, now remember they've given me 3 of the forces there. So I know I will have friction. Okay, I will have the gravitational force. Remember the gravitational force goes, works vertically downwards, or you can say this is the weight of the object. Right, but what else do I have? I've got the normal force. And the normal force is always perpendicular to the surface. So this would be normal force. All right, so this is really what I would have at the end of the day. Right, nothing wrong if you decided, and I'll draw them in as dotted lines. Instead of drawing that weight there, you could have the weight parallel, or in this case the parallel component of that force there, as well as the perpendicular component. So this would be weight perpendicular. Please note that when you draw those, please do not also draw the weight. So it's either you're going to have components or you're going to have the weight itself. Okay, so in my case I chose the weight. And for 3 marks, there are 3 forces, right? And then finally, they said draw a velocity time graph for the entire motion of the crate, starting from from point A until it passes point B. Right, so now, all right, they didn't say what we should show for that velocity time graph. If you don't mind, ladies and gents, I'm just going to try to remove some of the information there. I'm sure that you would have actually just understood that. Okay, so we're looking for the velocity versus time graph. Okay, so my velocity versus time graph. Okay, please remember velocity in meters per second. Okay, so let's make some space. Velocity, that's meters per second. Okay, and this is time. And this is in seconds. Right, now, if you look at this, we started with an initial velocity of 0, right? We increased at this point, we got to 5.83, so definitely that's what our graph does, right? We got to a velocity of 5.83, right? This is from A till C. Now, remember the rope snapped, and what happened? Right, so which means the velocity is going to decrease up until we get to point D, right, where we stop. Okay, so this would be point D over there. And then what happens? Then the trolley starts to slide back, right? So in this case, it's going to slide back. And what happens over there is that, right, so, okay, let me just try to make that into, right, so the deceleration that it would have would be the same as the acceleration that well, the same deceleration, by the way. Right, so this is when it passes point B. Okay, we don't know what that velocity is, but it should be greater than the velocity at C, and it is moving in the opposite direction. Okay, so this is what our velocity versus time graph looks like. So this is the velocity at B, should be negative. This is the velocity at, so this is at D, okay. This was at C, right, since we don't have all the times that are associated with that. Okay, and essentially that is our velocity versus time graph, ladies and gents. Okay, so we would have passed point C again at minus 5.83. Okay, and in that case, the velocity at B, as I said, was greater than the velocity at C. Right, and that is how the cookie crumbles, ladies and gents. Right, we're going to move on to question 6 next. And if we go to question 6, they say to us we've got a car that moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device which can both emit and detect sound waves. They say the device emits sound waves with the frequency of 24,000 hertz, right? Very important. I've highlighted it there. They say these sound waves are reflected off the car and the reflected sound waves are then detected by the device as shown in the diagram below. Right, so in this case, we are going to take that. They say state the Doppler effect in words. Right, remember that it is the apparent change in the frequency that is observed, okay, relative to the motion of the observer and the relative to the motion rather of the source and the observer, right? Okay, so they say if the sound, the speed of sound in air is 340 meters per second, they say calculate the frequency of the reflected sound waves detected by the device. So now, ladies and gents, remember we are transmitting 24,000 hertz over there, right? And in this case, because we've got a car, all right, so in a sense that our car is going to be the receiver, all right, of this frequency, right? So in this case, first of all, let's first find out. We're going to treat the car as though it was the observer. Right, so we're going to say, well, firstly, we've got 6.1.2 there, right? So the frequency of the listener, okay, is equal to V plus minus VL over V plus minus Vs times Fs. Now, ladies and gents, in this case, I know that the frequency, now if you note there, I would have had V, okay, we know that V is 340, right? Remember, our device is stationary, the car is moving, so the car has got a velocity of 22, right? But I want you to note, in this case, the frequency that the car picks up, right, would be higher because it would be moving towards the source, right? So this is divided by, now remember, our source is stationary, so this would be 340 minus 0, right? Okay, multiplied by the frequency of the source, this is going to be 24,000, okay, and that gives us the frequency of that is on the car, right? Now note in this case, what does that give us? Okay, so we're going to say this is 340, okay, plus 22, all of that divided by 340, that gives us that number multiplied by 24,000. 24,000, that gives me 25,552.94 hertz. That is the frequency that would have been picked up on the car, right? But remember, this now becomes the frequency. Now what we're going to do is use this as the frequency that the car now transmits back into the device, right? So we're going to say again the frequency of the listener. This time the device is the listener, right? The car is the source. So we're going to say, well, V. Now I want you to note that the source is the car is the source, and the source is moving, right? The receiver is stationary. So that would be V, and that would be V minus the velocity of the source, which is the car, multiplied by the frequency, of the source. Okay, so we're going to say that's 340 divided by, that's 340 minus, now in this case, please note, car moving at 22 meters per second, right? So that's multiplied by 25,552, and what would be the frequency in this case? Okay, so we're going to do exactly what we did before. Okay, so I'm going to multiply that. I'm going to put that in brackets, and say this is 340, 340 divided by 340 minus 22. So put that in brackets. Right, so the detected frequency would be 27,320.75 hertz, right? So that is what the receiver would actually detect. All right, now the next question, they say the spectral lines observed for a distant star show that the star is moving away from the Earth, right? Explain by referring to the frequency how one can deduce that the star is moving away from the Earth. Now, remember, ladies and gents, what we do is we are going to observe the gases of that star, right, that are in the star, right, relative to, or rather, we are going to observe the line spectra of the star, that is, of the distant star, relative to the same gas on Earth, right? And in this case, when we see that there is a red shift, that is, it shifts towards the lower end of the frequency, then it means that it would actually be moving away. Okay, so if the line spectrum of the gas of the star is moving towards the lower frequency end, or red shifted, if it is red shifted, right, then we know that it would be moving towards, actually I was trying to write frequency there, I wrote free, right, so the lower frequency spectrum. So in that case, it means that it is being red shifted, and so as a result, it is moving away from the Earth. All right. Okay, so question 7 says 2-point charges X and Y are held 0.003 meters apart as shown in the diagram below. The charge of X is 7.2, negative 7.2, exponent negative 9, while the charge on Y is 7.2, exponent minus 9. All right, so they say state Coulomb's law. In words, we know that the electrostatic force between 2-point charges is directly proportional to the magnitude of their charge and inversely proportional to the square of the distance apart, right? Okay, so they say draw the net electric field pattern due to the 2-point charges. Now remember, we've got a positive and a negative charge there. So definitely what we're going to observe, okay, in fact, let's just draw them as some type of spheres. Okay, so what we're going to observe there is that the pattern, right, I'll try to make it as nice as possible. Okay, we know there should be a force of attraction between them. Okay, and please just make it a point that when you draw these, you try to indicate the line density must show which charge is bigger than which, but I can see that both of them have got equal charges, so the line density on them, meaning the number of lines, should basically be the same, right? So what I'm going to show there is X is negative, so this would be X and this would be Y, right? So the lines are moving inside on X and they're moving away from Y. So I'm going to show that on Y, the lines are actually moving out. Okay, right, so that is what our diagram would look like. Okay, so the next question says calculate the magnitude of the electrostatic force that Y exerts on X. Right, so ladies and gents, to calculate that force, that's the force that X exerts on Y, that's KQX QY divided by R squared, right? So remember Coulomb's constant, that's 9 exponent 9 multiplied by the magnitude of the charges. So that's 7.2. Please note, in this case, it's not necessary for us to put the sign. Now, because the charges are the same, right, in terms of the magnitude of the charge, I'm just going to say 7.2 times 10 minus 9, all squared, right? Divided by 0.03, the distance. Please note that that is also squared. All right, so let's go and calculate quickly. So we've got 9 exponent 9. Note, I'm going to use that exponent button next to the answer button there on the left. Okay, so this is multiplied by, okay, we said this is 7.2, again, exponent, negative 9, and we square that. This is divided by 0.03 squared. Okay, I can actually represent this as 5.18, right? So this is 5.18 exponent. So that's 1, 2, 3, 4. And that's minus 4, right? Newtons. And since they said magnitude, that we will leave that right there. Okay, please just verify that that is correct, but it looks like I am correct there. Right, now they say to us a third point charge Z of unknown positive charge is positioned 0.01 meters to the left of the point charge X on the line joining charges X and Y as shown in the diagram. Right, now they say to us draw a vector diagram to show the direction of the electric fields at the point where X is positioned. Now, note, in this case, I want you to please note, we are placing a point charge. They said to us it is a positive charge. So if you think about it, what would happen to X? X would be attracted, right, by Z because it has a positive charge, but also X would be attracted by Y since it has a positive charge as well, right? So it means that the field, right, so this would be the field due to Y, okay, and we've got also the field due to X, right, due to Z rather, on X. So this is the field due to X on due to Z rather on X. So I'm going to, so EZX EY on X. All right, so again, what you could do is that you could take that vector diagram, okay, and just superimpose the one on top of the other, just to show it's not the same as a force diagram, but the concept is similar, right? So this is 7.4. Right, so in this case, they say to us the magnitude of the resultant electric field at the point where X is positioned is 4.91, okay? So remember that those fields, right, would be in two different directions. So as a result, there'll be one that is bigger than the other, and they will subtract each other. Right, they say calculate the magnitude of charge Z. Now, ladies and gents, what I'm going to do, now please, I want you to please follow me in this. I am going to say, well, the net field between the two, okay? Now, it doesn't, I'm not sure which one is bigger than which, but I'm going to take the direction to the right as positive, right? So the net field, now they said the magnitude of the resultant field at the point where X is positioned is 4.91, and they didn't say in which direction, right? So I know the net field, not F net, but E net, okay, will be equals to EXZ minus, okay, let me say rather minus EXZ plus EYX, okay, right, EZX and yeah, that's ZX, okay, so it really doesn't matter, ZX and YX, right, so we got that to be 4.91, okay, right, so in this case, I am going to leave that, and by the way, you know, honestly, they should have actually told us in which direction it is, so that's times 10 to the power 5, right? Now, EZX, in fact, I do suspect that the one on Z would actually be bigger, okay, so the net field should actually be to the left, right, because this one is actually closer in terms of direction. So I'm going to take a chance there, say, well, if I've chosen that to be negative, so which means my net field would be negative, right? So this is K, right? So note, I take the field of Z, so that's QZ, right? So that's minus KQZ divided by the distance between that is 0.01. Okay, 0.01 squared plus, we said that direction is positive, so that's going to be K QY divided by the distance between X and Y is 0.03 squared, right? Now, ladies and gents, I'm going to try and do as much as I possibly can. So that's negative 9 times 10, negative 9 times 10 exponent 9 QZ divided by 0.01 squared plus. So I'm going to take KQY in this case. So this is going to give me 9 exponent 9 multiplied by the charge on Y. Remember, this was 7.2 exponent negative 9 divided by 0.03 squared. Right, and this is equal to, I said the field there will be negative 4.91, and the reason why I said negative, because I said EZ should be much bigger because of that distance. So this is times 10 exponent 5. Okay, unless the charge on Z is really significantly larger. Okay, so I'm going to take that to the other side as well. All right, so let's whip out our calculator. So I'm going to say negative 4.91 exponent 5. Okay, I'm going to subtract it from, now remember, I've got that 9 exponent 9, so that entire fraction over there, okay, multiplied by 7.2 exponent negative 9, okay, divided by 0.03 squared. Okay, right, so I get that answer there, negative 563,000. Okay, 1,000 is equal to that entire fraction. Now, ladies and gents, how you choose to do this is really up to you. So what I'm going to do, just to make it easier for myself, I'm going to multiply by 0.01 squared and divide by 9 exponent 9, right? So I'm going to say multiply this by 0.01 squared, but divide this by negative 9 exponent 9. Okay, I get that entire answer. So the charge on Z, okay, you can work it out, please. I get a charge of 0. Okay, so because I'm not, let me just put it on math mode so that I can get it into scientific form. So my charge on Z, I get a charge, the magnitude is 6.26 times 10 minus 9 coulombs, right? So that is my charge on Z. You can verify it, ladies and gents. And remember, they did say that it's positive, so that should also be positive as well. All right, ladies and gents, that is how that cookie crumbles. I hope that you understood it. Okay, let's go to question 8. Moving right along, question 8, they say a battery with an EMF of E, right, and unknown internal resistance R is connected to 3 resistors, a high resistance voltmeter, 2 switches, and 2 emitters of negligible resistance as shown below. Sorry about that. Now, firstly, they say state Ohm's law in words. So remember that the current across a conductor is directly proportional to the potential difference, and provided that temperature remains constant. Okay, right. So in this case, they say to us both switch S1 and S2 are closed. Right, great stuff. So that means that we're going to be able to have current flowing in the entire circuit. They say the reading on A1 is 1.5. Okay, and in this case, they want us to calculate the reading on the voltmeter. Now, ladies and gents, if you've seen me do circuits, I always say, look, the first thing that I do is just try to analyze my total current, right, out of the battery up until I get to this point. And what happens? The current divides. So some of the current would go through that resistor there because the switch is closed. So that would be the current there. And then some of the current would go through that resistor there. Okay, so some of the current would go through that node. And then when we get to that node there, it's the total current again. And the total current is the sum of the two. So A2 would be the total current in our circuit, right? All right, so first of all, what does that show us? It shows us that we've got two parallel resistors or combinations, right? It shows us first that the resistors, so I'm going to give them names so that it's easier for us to make reference to them, right? I'm going to call this resistor R1, I'm going to call this resistor R2, and that resistor R3, right? So the same current flows across resistor R2 and R3. And what current is that? It would be that 1.5 amperes that is passing there, right? And the combination of R2 and R3 is in parallel with R1. Okay, I hope that is clear, ladies and gents. All right, so let's quickly have a look at it. They said to us, calculate the reading on the ammeter, right? So what do I know about resistors in parallel? Okay, I know that when I've got resistors in parallel, right, the voltage is the same. So I can find out the voltage across these two resistors over there, all right? So I will say, well, the voltage across resistor R2, or I can say the parallel voltage, that is V, right, will be equals to, right, let's call it I1, that's the current there, multiplied by the sum of the two resistors, that's R2 plus R3, right? So that would be 1.5 multiplied by, this would be 2 plus 5, which would be 7. Okay, so let's find that voltage V there. Okay, right, this is from our previous calculation. So that's 1.5 multiplied by 7. Okay, that gives me 10.5 volts. Now, note, ladies and gents, resistors in parallel have got the same voltage. So the voltage across these guys would be the same voltage across the 3 ohm resistor, right? So now I can find out what the current is across the 3 ohm resistor. Okay, I know that this seems like I'm going the long way around, but nonetheless, it is very safe, right? So now I can get that total current. There's another way that I'll show you just now when you've got resistors in parallel, right? So in this case, so I total, firstly, let's calculate I2. This would be now the current that's passing through the 3 ohm, right? So I2 will be V divided by R1. And so let's say 10.5 divided by 3 ohms. And so in this case, what does that give us for I2? That will give us 10.5 and 10.5 divided by 3. Okay, that will give me 3.5 amperes. And so as a result, ladies and gents, I'm simply going to say, well, on the reading, oh, actually, I'm busy with the reading on the ammeter, but actually they said the reading on the voltmeter. So essentially, ladies and gents, that's the reading on the voltmeter. Sorry about that. Okay, right. So I actually read question 2. And so they say now calculate the reading on the ammeter, right? So I showed you how to calculate the reading on the voltmeter. So for the ammeter, what I'm simply going to do, 8.2.2, right? Just like I shown you there. I am actually going to find the current that is passing through the resistor R1, right? So I'm going to say, right, that's I1, let's call it that, or rather let's call it I2, because we already said I1 is the one that's passing through the two resistors there. So that would be V over R. But now remember, in parallel, the voltage is the same, right? So that voltage is 10.5. It's the same voltage across these two resistors. So as a result, I2 would be 10.5 divided by that 3. And in that case, that's where we got the 3.5 amperes from. Okay, so this was me going ahead of myself. And now, to finish up the question, I total, which is A2, or we can say A2, which is the total current, will be I1 plus I2. So this will be 1.5 plus 3.5, and that will give us 5 amperes. All right, I hope that makes sense. So we know we've got 5 amperes of current that are passing through there. Right, so let's go to the next question, ladies and gents. They said calculate the power dissipated by the 3 ohm resistor. So remember, when I want to calculate the power, okay, so I've got the voltage and now I know the current. So really I can use any of those. So that's going to be P is equal to V times I. You could have used I squared R, right? No problem there. So that would be 10.5 multiplied by the current is, we said the current is 3.5. Right, so we could find it that way there, 3.5, 10.5, sorry about that. That's 3.5. That would give me 36.75. Remember, power is measured in watts. You could have said I squared R, okay, in which case it would have been 3.5 squared times the 3, right? We get the same thing, 36.75. All right, and that is how that cookie crumbles. So now the next question, they say switch S1 is now open. Now, ladies and gents, if I open switch S1, now please, I want you to listen very carefully. Right, the moment I open switch S1, it means this entire part of the circuit is now going to be non-existent. It's going to be removed, right? Because there's no current that's flowing there. Right. Now they say to us, switch S1 is now opened while switch S2 remains closed, right? Now this changes everything about our circuit previously calculated, right? The only thing that would remain unchanged would be the EMF value as well as the internal resistance, right? So they say to us, the reading on emitter A2 is now 3.64. Now you note it was 5 amperes. Now it becomes 3.64. Okay? So now they say to us, calculate the EMF of the battery. Okay? So now you remember, if we're looking for the EMF, so I'm going to say for 8.3, right? The EMF is I into R plus small r, right? So this is for the new setup when the battery isn't there, right? I mean, when the other circuit, when the other part of the circuit is not there. So the EMF would be, now note in this case, the total current. I know what that total current is. It is that 3.64. So that's 3.64. My total resistance in this case would be 3 because that's the only resistor that's there, right? Plus R. But you note that I've got two unknowns in this case, right? So I'm going to keep that as equation 1. Now, where do I get the other equation? Now, please, I want you to note. Remember, I still have the previous current when switch S1 was closed, right? So what I can do is say, well, in the previous, right, so before we closed switch S1, we knew the total current, right? We can find out what the total resistance is, right? So I'm going to say, well, R parallel for my previous circuit when switch S1 was closed, right? Remember, this is R1 times R2 divided by R1 plus R2, okay? And actually, let me say R1 plus RS, R series, right? The combination of those two that I added there. So R1 times RS. Oh, goodness. So that's R1 times RS divided by R1 plus RS. Okay. Right, so that's going to be 3 times 7 divided by 3 plus 7. Okay, so 3 times 7 is 21. 3 plus 7 is 10. So 21 divided by 10 will give us 2.1. So the resistance, the effective resistance of this entire parallel combination is 2.1. The total current was 5 ohms. So the EMF would be equal to 5 into 2.1 plus the internal resistance. Okay, right, so that's my equation 2. Let me check. Did they ask us? Okay, right, so firstly, what are we going to do? Let's try and find, we know that equation 1 is equal to equation 2, and this is because both of them have got the internal the EMF there, right? So that means that 5 times 2.1 plus R is equal to 3.64 into 3 plus R. Okay, ladies and gents, so we can work this out in the simplest way that you can do it, right? So this would be for me, right? So this would be 5 times 2.1. Okay, that's going to be, that's 10.5, right? 5 times 2.1. Okay, so that's 10.5 plus 5R is equal to, again, I'm going to have the same thing over there. That's 3.64 times 3. Okay, that gives me 10.92. Okay, if you don't mind, ladies and gents, sorry that I'm just having to write over that 2 there, plus 3.464 rather, R. Okay, so let's find our values for R. Okay, we're doing mathematical gymnastics. 5R minus 3.64, so that's 5 minus 3.64, that gives me 1.36 R. Okay, and I've got 10.92 minus the 10.5, and I get 0.42. So for my internal resistance, if I divide that by 1.36, okay, 0.42 divide by 1.36, okay, I get 0.31. Okay, please verify, ladies and gents, if I'm still on the right path. Okay, so now I've got the internal resistance. I can now find out what the EMF of the cell is. I can substitute into any of those two equations. So I'm going to substitute into equation 2. So the EMF of the cell would be 5 times 2.1 plus 0.31. Okay, so I'm going to say this is, okay, that's 5 into 2.1 plus 0.31. Okay, I get 12.05. Right, so that is the EMF of my battery. Okay, right, ladies and gents, of course, you could have worked it out in a different manner, and I hope that it's not confusing with all of the slatter that is going on, but you can actually just follow on. Right, and finally, they ask us, switch S is now opened while switch S1 is closed. Rather, switch S2 is opened. Okay, so they open switch S2, so which means that guy goes. Okay, while switch S1 is closed. How does the voltmeter reading change? Right, choose increase, decrease, or remain the same. Right, now I'm assuming that they are comparing this to when they had closed switch S2 and opened S1. Okay, so I want you to note, first of all, now that we've closed S1, what is our total resistance? Our total resistance in this case is 7, whereas it was 3 at first. Remember, once I increase the effective resistance, or in this case the external resistance, my V external automatically increases, right? But in this case, so my V external would actually change, right? So firstly, my answer there is, I will say it increases. So please remember that all the time, right? Once I increase that, so it will increase. Now let's explain, right? So I will simply say, number one, an increase in R external. Actually, I wanted to say R external, right? So an increase in R external, right, will decrease the current, isn't it? Decreases the current. Okay, so if I note there, so I is equals to V over R. So what have I done? I've increased R, and so I will decrease. Now note in this case, right? So what happens? But I know that V internal is equal to I times R, right? So R internal stays constant. Current has decreased, right? So therefore, V internal will decrease. All right, I hope that you can follow on, ladies and gents. So because of decreased current, right, this guy remains constant, okay? And so in this case, V internal will therefore decrease. And finally, so EMF is equal to V external plus V internal, right? Again, this guy remains constant. So when V internal decreases, therefore V external should increase. All right, that is really how we are going to give that explanation, right? I've mentioned this time and time again when we are doing circuits. I hope that you are able to follow on, ladies and gents. And now we are going to move on to question 9. Right, so we go on to question 9. So they said the simplified sketch below represents an AC generator with a coil initially horizontal between the poles of a magnet. That is X and Y are 2 points on the coil, while A is one of the poles on the magnet, right? So they say when the coil of the generator rotates clockwise, right, the 2 poles of the magnet, the direction of the induced current is from X to Y, as shown above, right? So they say to us, is A the north pole or the south pole of the magnet? Now, ladies and gents, please remember, you're going to use, because we're dealing with the generator over there, right, you're going to use the right-hand rule, right? So in this case, I'm going to simply say, right, so if you note, the current, that's the direction of your current. So that's your forefinger. That is the one next to the thumb. So it would be pointed in that direction, right? And now you can see that they're rotating this thing clockwise. So meaning your thumb would be pointed upwards. So think about it. So your forefinger is pointing that way. Your thumb is pointing in that direction upwards, right? No, sorry, not your forefinger, rather your second finger would be pointing in the direction of the current, right? So this is the second finger. The middle finger is pointing in that direction, the direction of the current, okay? And your thumb is pointed upwards. If you place them at right hand to each other, you'll see that the magnetic field should be moving from left to right. And the only way that can be is if that is north, okay? Right, so that would be the north pole, okay? They say the coil is now rotated 180 degrees. And of course, once we rotate it 180 degrees, the direction of the current will change. They say, will the direction of the current be from X to Y or Y to X? So it was X to Y at first, so now it will be Y to X, okay? Right. And then they say to us, sketch an EMF time graph for 2 complete cycles, 2 complete rotations of the coil, starting from the position of the coil as shown in the diagram above. Now, ladies and gents, I want you to please consider, right, in the position where the coil is sitting at, this is where I would have maximum induced current, right? So I'm looking for a EMF. So this is where my EMF would be maximum. So my graph is not going to start at 0, right? It would have been 0 if this thing was at 90 degrees, right? So what I'm going to do there, all right, maybe let me just draw it there. And remember, they said 2 complete cycles, right? So I'm going to have, okay, this is 1 cycle, okay, so, and another cycle would be exactly the same thing, okay, ending at that point over there, right? So this is going to be EMF, this is in volts, okay, and they said we are drawing the graph of EMF versus time, and this is time in seconds. Okay, right, so that is what our graph would look like. Okay, so now let's look at the next question. They say an electric device, okay, an electrical device is connected to an AC generator. The RMS potential difference is 200, so that's VRMS. And the maximum current passing through is 6 amperes. So that's maximum current. They say calculate the resistance of this device. Now remember, for me to get the resistance, I need to get my voltage and current to the same units, whether maximum or whether RMS, it doesn't matter. So in this case, I'm going to choose RMS. So I'm going to start with the current. So let's find I RMS first. So I RMS would be I max divided by square root of 2. So this would be 6 divided by square root of 2. Right, I'm going to leave it like that. Okay, so when we are looking for current, we've got the voltage V RMS. So remember, so in this case, I've got V RMS. Okay, let's do this. V RMS is equal to, I RMS times the resistance of the device. So all we need to do, ladies and gents, is divide by that current divided by I RMS to get the resistance. Okay, so R would be V RMS, so that's 200 divide by, so that's 200 over 1, divide by 6 divided by square root 2, and you know, in this case, I can say multiplied by the inverse, that's square root 2 over 6, okay? You could have done that just on your calculator like that. So 200 divided by my Imax, 6 over root 2, or you can say, I'm going to say multiplied by root 2 and divide that by 6. Okay, I get 47.14. Please verify that. Okay, I get a resistance of 41.14. Right, and then finally they say to us, calculate the energy consumed by the device in 2 hours. Now remember that for the energy, okay, I can say VRMS, okay, VRMS times IRMS times IRMS multiplied by the time. So I've got VRMS, we said that's 200. IRMS is 6 over root 2. And the time in 2 hours, right? It must be in seconds, ladies and gents. So this is going to be 2 multiplied by, now remember there's 60 minutes. A minute has got 60 seconds. So that's 60 times 60. That's 1 hour. Okay. So in 2 hours, it's 2 times 60 times 60, right? Okay, so let's find out what the product is over there. So that's going to be 200 multiplied by 6 divided by root 2, square root of 2. Okay. In fact, let me do this just to be 6 times 2 times 3,600. 3,600, remember this is the time that it takes, right? And this is all divided by square root of 2. And ladies and gents, as I continue to say, please, you can calculate this in the way that you find suitable for you. So I'm going to say that 6.11, okay, the energy is 6.11 megajoules, right? Megajoules, or you can say times 10 to the power 6, okay, joules. Remember that energy is always measured in joules. Okay, ladies and gents, and really that's how that question ends. Right, and finally question 10, they say in a photoelectric investigation, light of different frequencies was radiated on each of the two metals, A and B. The graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown below. Right? They say point X on the graph represents the unknown maximum kinetic energy. Right, they say write down the numerical value of the gradient of the graph. Now remember, guys, that the gradient of this graph represents Planck's constant, that's h. Okay, so that's 6.34, and you're given that value, by the way, times 10 minus 34. All right, they just said the numerical value, so I don't need to write down the SI units. Right, and the next question, they say define the term work function. Remember, we say this is the minimum energy required to emit electrons on a metal surface. Right, and then the next one, they say calculate the work function of metal A. So remember that the work function in this case, where are we going to get that? we know what the threshold frequency is, right? So the work function would be equal to HF0, right? The threshold frequency is 5. So this is going to be 6.34 times 10 minus 34 multiplied by, this is 5 times 10, right? Remember, to the exponent 14. Okay, so in this case, what do we get there? This is 6.34 exponent minus 34, that's Planck's constant, multiplied by 5 exponent 14. Okay, so right, in scientific notation, this becomes 3.17 times 10 minus 19, and that is in joules. That's the work function, right? And then they say to us, we need to calculate the value of x as shown on the graph. Now remember, guys, we've got the frequency at that value. So we want to find out what is the maximum kinetic energy at that point. So we know that we say E is equal to the work function plus EK max. So we're looking for EK max, right? But in this case, for E, we've got HF minus the work function, okay? So if we take work function, and that would give us EK max. So that would be Planck's constant, 6.34 times 10 minus 34 multiplied by 12.54 times 10 to the power 14, right? Minus that work function that we calculated there. So that's minus 3.17. Okay, I can't fit that all in there. Okay, so I'm just going to write it underneath. 3.17 times 10 minus 19, right? And that would give me my maximum kinetic energy. So X would be equal to, okay, so I already have that value, that 3.17. I know I'm going to end up with a negative answer, but I know in my case I'm going to make it positive. So this would be minus, okay, 6.34, okay, exponent negative 34, right, multiplied by 12.54 exponent 14. Okay, ladies and gents, I get that kinetic energy, right? As I did say, it was going to be negative. So let's, in scientific notation, X would be 4.78 times 10 minus 19 joules. I know your calculators are not as complicated as mine, so you should be able to get to that answer quick, fast, and in a hurry. Right, so that is how we get to that. Now quickly, the last portion, they say, how will each of the following be affected if light of frequency 12.54 times 10 to the power 14 hertz, but higher intensity is used? So if we were to use a light of higher intensity, remember, it will not affect the kinetic energy, but it will affect the number of electrons emitted per second, right? So they say choose increase, decrease, or no effect, right? So what should happen to the value of X, right? So there should be no effect on the maximum kinetic energy. And they say the number of photoelectrons emitted per unit time, that definitely increases. Okay. And then they say metal B has a larger work function than A. So now we are choosing another metal, right? So the larger the work function, So in that case, the more difficult it will be to emit electrons, right? So in that case, we will have, you know, a graph with a larger work function, right? So they say, redraw the graph above. In your answer book, do not include values on the axes. Label this graph as A, right? And then on the same set of axes, sketch the graph of metal B. Label this graph as B. Right, so fortunately, I already have the graph there. You would have to redraw it. Okay, so if it has a larger work function, ladies and gents, we don't know what that work function is. So which means, in that case, the threshold frequency would actually be greater. But remember that the gradients of the two graphs should be exactly the same, right? So this would be A over here, and this would be B over there, right? And essentially, ladies and gents, out of 150, we've earned our 150 marks, boo, 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 boo. Right? So that is really how the cookie crumbles. I really hope, ladies and gents, that you were able to follow on in what I did and that you really, really understood and enjoyed it. For those who are preparing for your exams, I wish you all of God's best. But of course, we keep working hard, right? And I shall see you guys again next time. Please don't forget to subscribe or share and recommend the channel to as many people as possible. Otherwise, I'll see you guys next time. Sharp, sharp.